Okay, so this video is intended for if you want some extra guidance on how to approach the challenge problems on 1.10. So here we go. Okay, number one, a player kicks a soccer ball toward the goalkeeper, at an angle of 37 degrees above the horizontal with an initial speed of 14.7 meters per second. Goalkeeper stands 26 meters. Okay, goalkeeper, he's got big gloves. 26 meters from the keeper or from the kicker. Where would the ball land relative to the goalkeeper? Okay, so this distance here, 26 meters. Okay, and here's our little kicker. He's got a big foot. All right. We need to figure out where is this ball going to land. So if we trace the path of the ball might land somewhere here. The ball might land somewhere behind the goalkeeper. We don't know. We have to figure that out. So we're looking for where does it land? Does it land that way? Does it land this way? Who knows? Where does it land? Okay, so you're going to have a number, either whatever this distance in front of or behind the goalkeeper is, and you'll say in front of or behind the keeper. All right, so how do we approach this? Well, we need to figure out our displacement. We need to figure out what is our displacement for the path of this projectile. So displacement equals question mark. All right, so in this displacement, right, we only, in the x direction, here's our displacement, x and y, we only ever use Vx equals displacement over time. Okay, so we're going to need velocity in the x direction and time. Well, we can get time, right? Time up is v naught y over g, and we have our overall initial velocity. We have our angle, so that means we can find the rest of this triangle. So v naught y, let's see, sine of 37 degrees is v naught y, because it's opposite, divided by the hypotenuse. So over 14.7, you can solve for v naught y there. Okay, so we have v naught y. We have it. All right, so once we have v naught y, then we can find for t using this equation over there. Okay, so now we have our time. All we need is our velocity in the x direction. Well, we can use our velocity triangle again. So Vx, velocity in the x direction. I'll bring this kind of down here toward the bottom, come back to the red pen. So velocity in the x direction, right? In order to solve for that, we're going to need in this triangle, this 37-degree angle and this 14.7 meters per second, right? So cosine of 37 degrees, because that's our x velocity, is the one that's adjacent to that. Cosine is equal to Vx over this 14.7. Okay, so once you go through, you can solve for Vx. We've solved for t. Now we can find our displacement. All right, so there's question one. Question two. In problem one, the goalkeeper watches the ball until it reaches the maximum height, then runs at a constant speed to intercept it at ground level. All right, so here it is. If you look at the answer for number one, the ball lands at some distance in front of our goalkeeper. He's happy because it's landing in front of him, not in the goal behind him. Oh, we still got those big gloves. Still got the big gloves. Whee! All right. So when our goalkeeper, he runs forward to get this soccer ball. How fast must he run? But he runs at a constant speed. Okay, so in this running, we have to figure out, right, our velocity of our goalkeeper. It'll just be whatever displacement he has to make up between him and the ball. We called that x on the last screen. In however much time it is that he runs. Okay, but he watches it until the maximum height. So it's right there is when he starts running. So in terms of our projectile motion, he has only the time from the top down to the bottom. We call that time down. Okay, so velocity of our goalkeeper is going to be x, whatever this distance is, divided by the time down. That's how fast he has to run. Okay, so it's up to you to determine the time down from situation in problem number 1. All right, moving on. Okay, baseball hit. So this is the required problem. All of you have to do this problem, regardless of which other 3 you pick. A baseball is hit at 30 meters per second at an angle of 53 degrees with the horizontal. Okay, 53 degrees with the horizontal. It's hit at 30 meters per second. The outfielder runs at 4 meters per second toward the infield to catch the ball. Okay, so outfielder, he runs at 4 meters per second toward wherever this ball is going to land. So this ball, here's our path of our ball. Okay, so there's the path of the ball. The outfielder has to run at 4 meters per second to get to this point where the ball is. We're looking for what is the original distance between the batter and the outfielder. Okay, so that is our question mark. This whole distance between the batter and the outfielder. Okay, so we can break this down into a couple of different portions of this problem. First, we're going to need to figure out the distance that the ball travels, so we've been calling that d, and we'll need to figure out how far the outfielder has to run. In problem 1 and 2, we call that x. Let's do the same thing. So here's problem x, x. So our overall displacement here, question mark, is going to be d plus x. Okay. So let's take this one step at a time here. This first half here, this displacement, we're going to use the same projectile motion stuff that we've done the entire time. So let's break this down into our x and our y components. So x and y. In x, we know that we need to find our displacement. We know that Vx is displacement over time. Okay, so we need velocity in the x, and we need our time. Well, we always use the y-axis to find time, so there's time there. Velocity in the x-axis. Oh, we can use our velocity triangle here. So in our velocity triangle, we have 53 degrees. We have 30 meters per second. All right, now what you can do Vx is 30 cosine of 53, and V naught y is 30 sine of 53. Here's a little trick. We like 53 degrees. 53 degrees is special because 53 degrees, oh, I drew that poorly. 53 degrees is part of 53, 37. This is a 3, 4, 5 right triangle. Okay, so 53 degrees and 37 degrees, hey, that's the same angle from problem number 1, is a 3, 4, 5 right triangle. Which means, okay, 30 is our hypotenuse, so 30 is basically our 5, so this is just scaled by a factor of 6, which means that Vx is equal to, it would be the 3 side, but it's scaled by a factor of 6, is 18. V naught y, it would be 4, but scaled by a factor of 6, so this is 24 meters per second. And by the way, if you plug in 30 sine 53 and 30 cosine 53, you'll get within 100th of these actual answers, which is kind of awesome. All right, so now we know our v in the x direction. We know v naught y, 24. So this is, by the way, we need to find our time total. But with v naught y, we can use time up as v naught y over g and just multiply this all by 2 to get time total. All right, so time total is just 2 times v naught y over g. Plug in v naught y, that's our 24. Plug in g, that's our 10. Okay, so it would be 2.4, but times 2, so 4.8 seconds. All right. So we have Vx, we have t, we can solve for our displacement. So displacement, awesome, we've got. Remember, what are we looking for? Well, we're looking for d plus x. Okay, we have d. Now we need to find x. Well, this outfielder is running in this direction, and I tell you that he runs at 4 meters per second. So he's running at this constant 4 meters per second in to intercept this ball. So x is whatever his velocity is times time. It's basically our same exact motion equations. But this is the velocity of the outfielder. So I'll do v sub OF for outfielder. Velocity of the outfielder times our time. Well, I tell you velocity of the outfielder is our 4. The time that he runs, well, that'll be the time that the ball's in the air, so that is our 4.8 seconds. So time, that's our 4.8 seconds that we have. Okay, now you can get x. Okay, so we have d, we have x. We can solve for the total distance between them. That problem is just conceptually difficult as far as what do I do? What do I solve for? So hopefully this video helped clarify. Please let me know if you have any questions. All right, we'll keep going now. So problem 4. In the 1968 Olympics, Bob Beamon shattered the record for the long jump with a jump of 8.90 meters. By the way, that's like getting close to 30 feet. 30 feet in one jump. Okay, assume his takeoff speed was 9 meters per second, which is that of a sprinter. How short was he of the maximum possible range for getting air resistance? Assume that G is 9.78. Okay. Because we're in Mexico City is honestly very high in altitude. So 9.78, this is the true number. Since I'm comparing the true number of 8.90 meters, well, let's use the true number of 9.78 meters per second squared in Mexico City. All right, so we've got Bob Beamon here. He's running, and he jumps. He jumps. We're told that he jumped a total distance of 8.90 meters. But we're looking for what would the actual maximum possible one have been. So this would be our maximum possible displacement here. Maximum displacement, so I'll just put d sub max. We're looking for how short was he. So we're looking for this total length right here. All right, so that's our question mark. Okay, so what we need to do, we're told that this is 8.9 meters, but we need to calculate the displacement of the maximum. We're also told that he jumped off at 9.5 meters per second. So if he jumps at 9.5 meters per second, all right, 9.5 meters per second. Here's my question for you, though. What is the angle for the maximum displacement? You guessed it, 45 degrees. So this is for this green path over here, for the maximum possible. This is our maximum, and it would have been at 45 degrees. Okay, so if we use our velocity triangle here, we can solve for v naught y, we can solve for vx. So v naught y and vx, you can use the normal sine and cosine to get those. I hope you're okay with those by now. Just as a reminder, that would be like cosine of 45, cosine of our theta is equal to the adjacent, so vx over the hypotenuse, 9.5. Adjacent over hypotenuse. The 9.5 goes on the other side of things. Adjacent divided by hypotenuse over 9.5. Okay, so you can solve for vx. V naught y, the exact same thing, just use sine. All right. So there's our velocity triangle. Okay, we have vx. We have v naught y. We have, what can we get from v naught y? Time up, but we really want time total, to v naught y over g. That gives us our time. Okay, so we have time. Wonderful. So we have vx, we have time. We can solve vx is displacement over time. We can solve for displacement. Okay, and this would truly be our d max. This is for this green line here. So whatever this d max is, whatever you get for your D max minus 8.90 meters, that will be your answer, because that's the difference. That's how short he was of the maximum distance. All right, moving on. Number 5, helicopter is rising vertically, or this should say a helicopter is rising vertically at a uniform velocity of 14.7 meters per second. Okay, so we've got a little helicopter here. Little helicopter rising at 14.7 meters per second. So 14.7 meters per second. When it's 196 meters from the ground, okay, so 196 meters, 196 meters from the ground, a ball is projected from it with a horizontal velocity of 8.5 meters per second. Okay, horizontal velocity, that is, it actually tells us right there, Vx. So this is kind of weird, but I'll hopefully walk you through it. Because the helicopter is rising at 14.7, and then we throw something sideways, but whoever throws something sideways is also rising, so the ball's motion is going to be up, like that. However, okay, so this is really the first problem we've looked at where the velocity, oh, that's not the pen I want. The velocity, or sorry, the height that it starts from is not the height that it ends at. The height it starts from is not the height that it ends at. So I'll make this line here to say, okay, this point is even. So I'm going to divide this into 3 sections, time 1, time 2, and time 3. We know that time 1 equals time 2, but we have no idea as of this moment how time 3 relates. Okay, so calculate, first of all, when the ball will reach the ground. Okay, so when the ball will reach the ground, we're looking for time total here. Actually, I'll do this in a different color so as to not confuse you with the individual times. Let's do orange. It's almost October, right? So time total equals question mark. Well, which axis do we use for time? We want to use the y-axis. All right, well, we have our initial velocity in the y. That's what the helicopter was moving. Okay, so v naught y is 14.7 meters per second. We know our acceleration, negative 10. We know our initial height. We know our height that the ball travels from start to finish. Well, it moves down 196 meters, so negative 196. Okay, so we can now use our equation because we're looking for time. All right, so height is equal to v naught t plus 1/2 at squared. Go ahead and plug in your height, plug in your velocity initial, plug in your acceleration. I'm sorry to say you will have to use quadratic equation on this one. Yes, I know, how terrible of me, but yes, you have to use quadratic equation, then you get your time total. Once you get the time total, then you can just compare it with velocity in the x direction. That will show you how far it goes left to right. And then what velocity will it hit the ground with? Okay, well, we'll have to get v final y at this point. We know v in the x direction because that doesn't change. So just use Pythagorean theorem. We can find our overall final velocity. All right, number 6. Number 6 is actually very similar to number 5. I'll let you kind of work with that. If you need any extra help, please do let me know, but it's very similar to number 5. I hope you at least attempted one of these problems. If not, make sure you do now. All right, let me know if you have any extra questions. Otherwise, see you in class.